Hello everyone, we are presenting our final project, Smart-RTC for CS566. This is a joint work with Shige, Shuqi, and Yijia. Here is the overview of our interface. We will introduce more in our demo. We will first introduce the basic WebRTC. Then we will illustrate how we reduce the packet loss by adaptive resolution. Lastly, we will introduce our highlighted features that contribute to our smart WebRTC.
Hello, so in this part, we're going to introduce the basic implementation of our WebRTC application. So we set up a signal server, which is responsible for maintaining many chatting rooms and establishing peer connections between users in the same room. When users request to create a room, the server will create a room instance and track users who join this room. When users request to join a room, they send room IDs to the server, and then the server will return the current user ID list in this room. Then the new user will establish peer connections with each of these current users. This process consists of new users sending offers and the current user sending back answers, and then the new user exchanging the ICE candidate with the other current users. All of these messages are transferred by the signaling server. Finally, with the help of the ICE candidate server, new user can establish a direct connection with each of the current users and sharing video and audio streams using the connection. So this is the overview of our basic implementation. And now we're going to introduce the performance metrics that we're going to use in our experiments. So to evaluate the performance of our WebRTC application, we use 6 metrics as shown on the screen. To get the corresponding metrics data, we use statistics APIs, which are provided by WebRTC. It could provide the network statistic report based on each peer connection. Since our objective is to optimize the video stability and the user experience, we mainly focus on the first metric, frame per second, and the second metric, packet loss rate.
So here are the evaluate results for our initial WebRTC. With an increasing number of users in the same room, the FPS for each user drops below 30, which is the default maximum value configured by WebRTC. The maximal user number in our evaluation is 15. Additional data analysis details will be included in the reports. Upon user leaving the room, the FPS gradually recovers to around 30 frames per second. Some normal fluctuations are observed during this process. The change of package loss rate follows a similar chain. Notice that there are values over 100%, which is the result of a synchronized nature of WebRTC statistics API. Therefore, the values may not be updated immediately. If the calculations are performed before the new statistics are available, it can result in inaccurate results.
Now, since we have found some problems with the current initial WebRTC application, now in this part, we're going to introduce how we propose adaptive resolution in peer connection to improve user experience and some other problems. Since each pair of users within a room will establish a peer connection with each other, assume that if there are n+1 users in a room, each user will receive n video streams. However, the download bandwidth of a user is limited. So if n is too large, the bandwidth allocated to each stream will be too small to maintain a stable video live stream. Thus, the channel bitrate, which is a product of FPS and resolution as shown on the graph, So, which is a product of frame per second and resolution times the constant, is also limited to a small upper bound. We aim to optimize user experience by maintaining a stable FPS. Thus, we implement a video adapter which can monitor established estimated bandwidth of current peer connection and dynamically adapt the video resolution to provide a stable FPS in stream.
Here is the result after we add our proposed adaptive resolution optimization. And we can observe that as the user number increases, the FPS maintains its value around 30 frames per second. And package loss rate also performs stable, surrounding 0. Therefore, we can conclude that our proposed method did help to provide user better fluent video streaming experience. And here is some new features provided by our Smart-RTC. Chatbot module implements the real-time text communication among clients. The example is shown on the right image. First, the user 5 sends the text, and the text message then will be sent to the signaling server with the user ID. Then the server will broadcast the user text to the other clients in this room. For each other client, then will receive the text message and show in their chatbot. The chatbot module does not depend on the peer connection.
To enhancing the intelligence of our Smart-RTC, we'll introduce our second feature, the Creative Whiteboard. This tool adds idea visualization by allowing users to share their concepts seamlessly within the room. Our first feature is text-to-image. In our first input box, users can type their creative ideas. A single click activates the model, generating an image aligned with the user's idea. As an illustration, inputting a river in the forest produces an image of this description on every participant's creative whiteboard. But what if someone desires to refine this image? Enter our second feature, image-to-image. Users can input specific instructions in the second input box, prompting the model to assimilate the current image and implement the desired adjustments. For instance, by typing "turn the leaves yellow," the model dynamically updates the original image, providing a dynamic and interactive platform for collaborative creativity. Let's dive into the operational mechanicals of this process deeper. For the text-to-image model, on the left-hand side, when a user submits an idea, the server starts the execution of a Python file of the text-to-image algorithm. Once the algorithm generates the image, it is securely stored in the server's directory, dedicated to each specific room. Following this, the server broadcasts the URL of the newly created image to every user within the room. While the server is actively running the text-to-image algorithm, the sending button for all users is temporarily disabled. This step ensures that there are no conflicts during the image generation process, preserving the integrity of the collaborative space. The same streamlined process is applied to the image-to-image functionality. Our final standout feature involves empowering every user to download a text file of the chat box and all generated images. To export chat conversations, the client-side functionality takes center stage. It directly transcribes the current content in the chat box into a text file, saving it on the user's local device. For image downloads, a user initiates the process by clicking the button. This action triggers a request to the server, prompting it to efficiently compile all images in the room into a zip file. And the server responds with a zip file for the user to download. download. In a security conscious approach, the server ensures the removal of the zip file immediately after transmission. Moreover, as part of our commitment to privacy, when all users leave a room, the server erases all images associated with their room. This is all for Smart-RTC. We will provide more details in our demo. Thank you for your time and attention.